Our next speaker will be Michele Polose, who was already here on the panel before, so we'll content myself with a short introduction. He is a principal research scientist at Northeastern University in Boston, and his research interests on 5G, 6G wireless networks, millimeter wave and terahertz communications or mobile networks, and in particular also Open RAN and open source networking software. And as such, he will now talk about Open RAN GYM, enabling AI and ML in Open RAN.
Thanks, Robert, and hi again. The idea that I have for today is to follow up on what we discussed on the panel this morning on Open RAN GYM and on some of the data needs that Kaushik also just mentioned, and tell you a little bit more about this framework that we call Open RAN GYM, and that we see as a sort of an end-to-end platform that allows you to do experiments with AI and ML in Open RAN. And I have to acknowledge all of the people that have worked on this, including Eugenio, who is upstairs. And I'll be happy to. I'm happy to tell you that by the end of this presentation, you'll know that there is even a fourth way to connect Eric over to OAI. But yeah, we can talk more about this offline. So this is the traditional illustration of the ORAN architecture, right? And I highlighted 3 innovations that have been discussed yesterday, today, and so on, which are like basically open and standardized interfaces, the disaggregation, the fact that you can bring in smaller, maybe open source contributions. But what I'll focus on is a 4th innovation, basically the RAN intelligent controllers, which I think are one of the key pieces of innovation in ORAN. And specifically, RAN intelligent controller enables closed loop control, right? So you have these intelligent control loops that basically run at different levels of your network. Some of them are standardized by ORAN, some of them are for further study, okay? So in the ones that are currently supported by ORAN, you go from periodicities which are above a second for no real-time control loops that mostly relate to policies, models, slicing at a high level, like with infrastructure level KPIs and so on. The second set of loops is the loops that run between the near real-time RIC and the E2 nodes, the CU and DU, and these run at near real-time, so 10 to 1000 milliseconds. And this is where you do closed loop radio resource management. So you can do load balancing and over, run slicing and so on. But something that we have been thinking about for a while is basically how you enable what ORAN now consider for further study, right, or not supported. So basically loops that run at the TTI level below 10 millisecond or even below a millisecond. But for the sake of time, I'm not going into this part. So what I'll discuss are mainly how we address these 3 challenges. So the need for a large-scale dataset which are heterogeneous, so that they really represent different kinds of deployment scenarios and so on. The need to test, as I was mentioning in the panel, the control loop without compromising the network performance, and the need for algorithms that generalize to different scenarios, different conditions. You may want to deploy your slicing XApp in downtown San Diego and in downtown Boston. It's 2 different environments. So what we did to address this is first an infrastructure component, and then we have been doing and we are doing some XApp development on top of that. And I'll focus first on the infrastructure component, which is what we call Open RAN GYM, which is this frameworks that enables these Open RAN driven experiments in large-scale experimental tests. That's Colosseum that was mentioning earlier, and I'll give a couple of words on Colosseum, the Power platforms, basically any software-defined testbed that supports one of the software-defined runs that we use. So you can collect through this framework, you can collect data at scale on Colosseum, specifically on virtual RF scenarios. So you can run the same experiments and swap the emulated wireless scenario. And we have, for example, Boston, downtown Rome, Italy, various RF scenarios that we can use. Then you can take this data, train your machine learning component, package it as an XApp quite easily because we provide some wrappers that allow you to do that, and then test it on and possibly refine it on wireless platforms. And I'll give you a couple more words on what I mean with refining. So this is the overall vision, and practically OpenRunGym, for which we have this website where you can go basically to find any information that you need, is a set of multiple components. The first one is a rig that is basically the OSC rig that we strip down at the basic components that you need, and we deployed on a Colosseum LXC container. So Robert decided to go one way, basically with writing an independent rig. We decided to remove the Kubernetes part and just leave the Docker containers, some of the containers that are needed. So you have the issue termination, issue manager, internal routing, a database, and then you can add any XApp that you need. And we provide some automation to help out in this. The second component is at the run side. So basically a framework to enable large-scale data collection and control of base stations. So for example, to collect just to make an example, we've been collecting data sets with around 10 base stations and 50 users, okay? If you want to do this with a software-defined testbed, you need to orchestrate 50 users to start exchanging traffic, 10 base stations. And if you have any experience with software-defined radios and OAI, SRS, and so on, doing this for 50 nodes or 60 nodes is a little bit of a pain. So this is why in Colosseum, we provide this automation that we call Scope to do the orchestration of the experiments and eventually the data collection, because all the logs are moved in a central location. We have the programmable software-defined protocol stacks, SRS, OAI, and you can run all of this on top of your publicly accessible experimental platforms or in your lab testbed, because we provide the components already packaged for this platform, but also each single component that you can take and deploy on your infrastructure. So you've heard Colosseum being mentioned many times. I'll just spend a couple of words to tell you what it is. At its core, Colosseum is a very powerful hardware-in-the-loop network emulator. Hardware in the loop in the sense that it uses 128 software-defined radios that can be individually controlled through a set of 128 servers by the experimenters. These radios are all meshed together. If you see, this is just a very high-level overview of the architecture, but these are all meshed together. And do you have a laser pointer? No. Oh, okay. Okay, so the radios are all meshed together, basically to create a through this component that we call massive channel emulator, and is a channel emulator that can basically emulate in real time up to 65,000 wireless channels, right? So you can run these experiments in Colosseum with, for example, with OAI, with the base station and the soft QE, and this is why Florian was mentioning that we are particularly interested in that line of work. And do your experiments with different kind of virtual scenarios, right? So basically create and test complex 5G scenarios. And on top of this, we have some additional compute infrastructure, for example, servers, NVIDIA DGX servers to run AI and machine learning, for example, to do the training in place. So something that we have developed for Colosseum and, for example, the Power platform is the capability of moving the operand gene framework across these testbeds. So you can start from an initial design at scale on Colosseum with different wireless scenarios. And if you want some validation over the air, you can move it to your indoor over the air lab, or specifically we usually move our experiments to Arena, which is an indoor test bed that we have at Northeastern with a similar structure of Colosseum. And then once you're confident that it works, you can move it in the wild to the power platforms, to like any other large scale test that you want to use. And this is just to show you an example. We did basically a couple of experiments. In this first one, we were manually changing a slice profile between two slices, and we deployed it on four different platforms: Colosseum, Arena, Powder, and Cosmos. And the quantitative results, of course, are different. There's different kinds of radios, there's different kind of propagation environments, but the qualitative results are the same. So this is manual, and we also tested an XApp that basically does joint slicing and scheduling control in near real time with a deep reinforcement learning agent. We trained this XApp in Colosseum, and we moved it again to Arena, Powder, and Cosmos. And you can see that, again, the quantitative results differ, but the qualitative behavior with basically the EMBB slice picking up when we start the XApp, the qualitative behavior is the same, right? So the results are, this is just to show that you can move your experiments and that the results are consistent across different kind of heterogeneous environment. Just to show you an example of a deployment that we did on Colosseum, we were using this wireless scenario, which is the basically 7 base stations around the real Colosseum in Italy. And we were using 6 users for each base station, so a total of 42 users split across 3 slices. And basically, we were controlling this network with the operand gene real-time rig to do different kind of things. And specifically, something that I'll give you a couple of details here. We were doing some slicing and scheduling control of the scheduling policy, so tuning of which scheduler can be used for the different slices. And we did it through this XApp that we designed as modular with a couple of components. So the first one here is an interface to the rig that takes care of all the boring ASN.1 thing that as researchers, maybe you don't want to get into. And the second component is the actual logic, which specifically here was a DRL agent. But in the sample XApp we provide, you have these, basically you have the rig interface and you have a stub where you can plug in your own logic. So we took this, we trained the agent and the autoencoder, basically the machine learning components offline, based on data sets that we collected on Colosseum. And then we moved them to Colosseum for testing. We recorded some performance. We noticed that there was an improvement in performance in terms of different KPIs for each slice, and we were happy. And then we asked ourselves, okay, this agent is trained with a data sets that represent certain network conditions, right? This is, as a result, it selects policies. These are basically scheduling policies. These are slicing policies with a certain probability. What if there is an unforeseen condition? What if we change something and the agent basically sees a new state of the network that was not seen during training? So what we basically did in response to this was fine-tuning the reinforcement learning model with online training on the near real-time rig itself, right? So we basically introduced a couple of changes, okay? So this plot is basically showing you your loss in the training, and here you have the reward of the agent, okay? So we do a couple of things. The first thing is we change the user traffic. So here the users were exchanging traffic as you would expect from users in a URLC slice or an MPC slice or in an MVB slice. And once we change the traffic, all the users use the same kind of traffic model, which is a sort of artificial change, but we just wanted to see how the agent reacts. So you see, you get a drop in performance, but when we do some online training, so we retrain the agent, and you see that it starts picking back up again. The second update that we do is we move the experiments from Colosseum to Arena, what I showed you earlier, right? And interestingly, here, the performance remain more or less the same. On Arena, it decreases because we are using half of the users that we are using in Colosseum, so the reward is divided by 2, but it is consistent with what we were seeing earlier. So this is just to show you an example of some kind of studies that you can easily do using this OpenRanging framework, right? And these are the kind of studies that also Kaushik was mentioning that are necessary to understand how you can and need to design machine learning solutions for OpenRun that are scalable, that can generalize well, that can adapt to unforeseen conditions. Okay. So this, I showed you this just to show you this, let's say, example of use case. Now I'll spend a couple of words on actually the infrastructure components, and specifically I'll talk a little bit about the kind of issue interfaces that we have on OpenRanging. So traditionally, the first release that we did last spring supported SRS LTE, so boo, right? Over the summer, we added something else. So support for simulated base stations, again, using a standard compliant E2 termination inside the simulation that you can connect to a rig outside of the simulation. This is something we did in collaboration with Mavenir. And today, I'm happy to tell you there is a fourth way to connect OAI to a near real-time rig, which is this kind of support for OAI base station with the OpenRanging, and eventually it's the same thing, the OSC rig. So just to show you an example of true interoperability, here I have on the top, I have my SRS LTE E2 termination. At the center, I have 5 E2 termination for NS3 for 5 simulated base station. At the bottom, I have the E2 for AI, and they're all connected to the same OpenRanging rig at the same time, where the termination is based on the OSC rig. So basically, base stations that start with 3131 are from NS3. This is the SRS base station, and this is the OAI base station. Okay. So we decided to do this with multiple support for multiple run for a number of reasons. So ease of use. So we provide some building blocks, the end-to-end connectivity, and then the user can pick which components they want to use. The idea of using the same rig infrastructure to support different runs. And also we decided to basically stick with the OSC rig because it's widely adopted by industry, and we've seen also in some academic environments. So we decided to stick with this rig to have sort of reference that other people are also using. OpenRanging is kind of easy to extend for fast prototyping and testing. Not only the XApp itself, but the service models are, I'll show you, are quite easy to understand and extend. And for the Colosseum and the Power platforms, this comes already prepackaged. So we have users that, for example, book some resources on Colosseum and can select to deploy the OpenRanging brick and some base station and do experiments with these components right out of the box. So the specific E2 support for, and I'll lead to the conclusion, the specific E2 support that we have for AI is based on protobuf for the service model, which we selected for a couple of reasons. the idea is that we wanted to avoid ASN.1 for the service model part, because we want to give it to the users. We want to let our users basically experiment and change potentially the service model to test new things. Okay, so this is the main reason why we went it for protobuf. We have an issue agent that is similar to the issue agent that we're mentioning earlier. And we have the sample XApp that I was mentioning earlier, where we provide already the boring components, and we leave you the custom logic to develop. So all of this is again on the OpenRangine website. There is a tutorial section that we recently added with step-by-step instruction on how to run an end-to-end experiments. And yeah, this is it. I hope I gave you some ideas of how you can do end-to-end machine learning experiments using overrun components. Oh, hi, nice to meet you.
A couple of questions about OpenAirInterface. I'm very excited to see that actually this is available. When you were running deep machine learning with actually near real-time prototype like OpenAI, right? It certainly run into the timing issues. Sometimes systems don't execute fast enough, or the training part, right? It's not fast enough for real time. So I wanted to hear from you a little bit about that part. And it is that are we able to actually integrate this with utilizing something like Ray for more scalable training? Ray, RAY. Right.
Oh.
Okay. So if you're not, that's fine, but
Okay.
the timing issue is very interesting. Thank you.
Yeah, so on the timing issue with the XApps that we developed, we've seen them basically controlling the scenario that we were using with a loop that was closing in about 100 milliseconds without doing any optimization on the Python component that is running the machine learning code. So there are definitely ways, I think, to close the loop in a time that is manageable for the near real-time periodicity. And we were also running quite complex reinforcement learning components, so that was not trivial. And for the second question, maybe we can take it offline, but in general, we are thinking at different ways which you can collect data for your training. You can use Colosseum. The NS3 component is another component that we introduced to give, of course, it's simulated, it's not emulated or over the air, but still gives you another level of flexibility in terms of how you can collect your data for the experiments, and they all use the same interface to the RIG component. So we think that helps.
Thank you, Michele.
All right. Thank you very much. Yep.